Thank you very much, Anton, for introducing me, and thank you very much for everybody to come into this seminar. It's a big pleasure to be in Turin. Actually, it's the first time for me to be in Turin, and I was from Monday attending 3 days of the conference, which is completely another topic, HMM as hysteresis modeling and micromagnetics, but it gives me exactly nice opportunity to visit some colleagues in Politecnico, to Torino, and I know Anton Proskurnikov since, I think, 2015, MICNON, IFA conference. So we figure out that some seminar more related to robotics and to mechatronics, to, let's say, applied control might be interested to some audience here. Okay, once again, I'm full professor at University in Agder, which is in the South Norway, and now I'm in my year sabbatical, just south part of Italy, Politecnico di Bari. What I'm going to talk today, and again, I have also much appreciate the possibility given by this seminar series of IEEE Control System Society chapter of Italy, which is like technically co-sponsoring this seminar. And the topic is on the screen, and we will look, because impedance control in robotics is something quite known. So there are very well accommodated approaches in the textbooks by people like Bruno Siciliano, Mark Spong, and a lot of co-authors. But what I would like to discuss with you today and show some interesting principles and also experimental results, that actually from the input-output point of view, for the standard linear control theory, which is using transfer functions, Laplace domain, sensitivity functions, open loop shaping methodologies for designing the feedback control, it is also possible to achieve some quite transparent and visible approach how to shape the force and impedance control and how to apply it at least with 1 degree of freedom. We will see examples just like think about some manipulator, only one translational degrees of freedom, but the principles are there, and we will see how it can be done for impedance control in robotics. Okay. So let's start with this. It's outline of my talk. First of all, we will remind and we will recall what is actually loop modeling and loop shaping from standard linear control theory perspective. And then we will compare the principles of impedance control versus the disturbance sensitivity. And we will see that the disturbance sensitivity function is one of the key, let's say, parts which are directly or can be directly linked to impedance control. And after that, I will show you quite a detailed case study, experimental case study, with contact transition, and where we will see that we are able to drive the stiff motion control, have the contact with some soft tissue, with some, let's say, penetrable and fragile materials, and stop without disturb them, without penetrate, and just think about potential applications of robotics in medicine, where you have some robotic assistant systems for surgery, and definitely you don't need to cut some very soft tissue. Think about any type of penetration in the human bodies and surgery robotic assistance. Okay, but first of all, I take this illustrative example. It is from classical textbook from Ostrom and Murray, 21. You can find second to third edition. What does it mean, closed loop specification and shaping? And here we see that we have standard notation. We have the plant transfer function P. We have already given design controller C. And then you have a part which is associated with process, and correspondingly you can have additional noise, matched input noise V or output measurement noise W. And then if you think about 2 degrees of freedom controller design, you can also have the feed forward path F. And then it is quite easy to interpret that if you have the given feedback control already, C is specified. Think about PI or PID controller. And then you have the specification for closed loop system from reference R to output Y. So you actually know what you are expecting. by specification, by application. Then it is quite easy applying just the block diagram algebra to determine what will be the, let's say, pre-filter or kind of feed-forward path, control path F, because it is directly out from knowledge of P, C, and G, Y, R transfer function, okay? And this is classical academic example. I use it also in my classes, and it is from the textbook. Let's take a look on the system of third order. So we have the plant just with 3 first-order time delay systems, everything stable, three poles in the same location. Then let's think about the PI controller, okay? And then let's see how it will be the response of such system without feed-forward and with feed-forward. Because if you have without feed-forward some transient oscillation here by blue line and in the frequency domain that we see 0 decibel, 10 power 0 is 1, 0 decibel, okay? Unavoidably, we are expecting some small resonance peak and transient. And if you want to be free from such transient peak and some transient response in blue, which is not satisfying, then designing the feed-forward path, we are like injecting additional dynamic in the total closed control loop from R until Y, and we can certainly improve and reach, for example, like here by red dashed line, the response with feed-forward. So this is very illustrative. This is very straightforward. This is known. And next, what I would like to explain, continue on this way of thinking, is actually that we have in such closed loop shaping by specification, we have a kind of reverse engineering, if you would like. Why? So first of all, we can have given specification of the closed loop system, and from some basic courses of master level or maybe advanced bachelor level control theory, you might know that oftentimes it is also known in industry, approximation of the closed loop control system can be the second order system where you have only 2 parameters. You have the natural frequency omega n, okay? And from the closed loop system, you are expecting 0 decibel. So it means that in the last part of the denominator and the numerator, we have omega n square, the same term. So at steady state, the transfer function GCL has value 1. So it is unity transfer function, okay? And the second parameter is damping, so damping criteria. And if you will allow by specification, for example, the damping of 0.7 to have only 1 overshoot, and after that, transient response without oscillation, then we will end up how our natural frequency omega n and damping zeta are expressed in terms of time constant T1. So if we are assuming it, then we will have our closed loop transfer function, which is still specification, expressed in terms of what we have on the right-hand side with capital T1. And what is interesting, that now if you will additionally introduce the gaining factor K, and it will be the gaining factor for the open loop transfer function, then the same in blue closed loop transfer function will have this form. And why we made this, let's say, mathematical gymnastic to obtain specification what we already had. It's not by chance, because now we can see how the open loop transfer function looks like, which correspond to this closed loop transfer function. Now my open loop transfer function has exactly one free integrator and has also one transfer element with time constant T1 and gaining factor K. This is a kind of universal specification for second order system. And this is quite known in classical feedback control theory, that for shaping the loop meaning the L transfer function, we can think about that we have at low frequencies some bounds related to steady state accuracy. And in the ideal case, for at least step type response, we should have one free integrator, what we now have in L. Then we have sensitive region of crossover frequency, because it is important for stability and also shifting to the right or to the left, it is related to performance. And on the right-hand side of such frequency response function of loop L, we have the upper bound related to uncertainties, to non-modal dynamics, to any types of high frequency noise, and so on and so on. Okay? And now we have been only doing the specification. But if we have the specification and if we know how to shape the open loop L, it gives us, let's say, ideal control. Directly the controller to be designed, C, is actually loop transfer function multiplied with inverse of the planned transfer function, because planned is actually given, right? But the problem of such control, which is can be seen as ideal, it turns to be maybe not realizable. And this is a very simple example explaining why. Imagine we're assuming for planned third order system with one free integrator here given by transfer function P, two time constants, they are different by order of magnitude. Think about slower dynamics of some manipulated body, and think about additional dynamics of actuator. So you have different time constants, right? And then your loop transfer function L is exactly on the right as we wished to have it in such ideal design. And then our controller, which is resulting here, C, has actually the order of numerator, which is higher than the order of denominator. What does it mean? It means that the transfer function of controller is improper. We cannot implement it. So we will need some additional adjustments, some low pass filter, or some additional, let's say, strategies for loop shaping. But in ideal case, the message is that if we know what we are expecting from the closed loop, after that we know what should be our open loop transfer function. And if we have the planned, then we can synthesize very straightforward and directly the linear feedback controller. All that on the two slides is very well known, and I guess it should be somehow accommodated in some control theoretical course you might have heard in bachelor or master, or seen at least in several textbooks. And let's also recall, because we will need better understanding what is under the loop shaping, let us recall what is actually the loop transfer function and what are the restrictions, okay? So before we are closing the loop transfer function L has actually all elements connected in series together. And in ideal case, it is only the plant and controller. But think about more boiling down and going to realization. We can have also additional parasitic dynamic of actuator. We can have also some additional dynamic of sensor. We might need additional some filter. We might also have unavoidably some additional time delay elements in the loop just because of the communication. If you're thinking about remote control with Wi-Fi technologies, or we are implementing our control decentralized and we are using the network. So actually everything sitting in the loop before we are closing it belongs to the loop transfer function. Okay, and now the, let's say, strategy or way of thinking, we would like to have possibly large loop transfer function in amplitude response, so much larger than 1, for frequencies lower than crossover frequency, okay? And at the same time, and this is for performance, for our reference tracking, but at the same time, we want to have roll-off and possibly low loop transfer function at higher frequencies. And how we specify the higher frequencies, we say it is starting from crossover frequency and most sensitive and most important, that we have to look into the frequencies where actually we could have also crossover of the phase response, minus 180 degrees. Because what we see here is only half of the story, it is amplitude response. But you might remember the stability criteria, gain margin and phase margin. So the another point where the phase response is crossing minus 180 degrees is critical as well. So we have two of such, let's say, desirable tendencies how to shape the loop L, which can also be in contradiction. And why it is a contradiction and why it is always the trade-off when shaping the loop? Because if we take the closed loop transfer function GCL. And if you take what is called sensitivity function S, and we will pay special attention to S, then they're in duality relationship in the sum they are 1. And this is very well known, and more deeply, if you are interested, look what is called body integral, and especially analysis of sensitivity function with respect to the body integral. But this relationship GCL plus S equal to 1 is not the question of the plant. It's not the question of control, whichever, let's say, intelligent control you might think about. It is a natural restriction by the feedback loop. So it means once we are talking about the feedback control, this is always valid. And now we will see why it is restrictive. Because, first of all, we need to remember what is the sensitivity function. It is the relationship between the reference and control error E. And in terms of relationship to the loop transfer function, it is 1 over 1 plus L. And now if you will start to analyze the control error E, we can imagine that our closed loop transfer function has actually two inputs. One input is the reference, and another input will be the matched disturbance on the input to the plant. And they are independent from each other. There is no correlation between reference. Think about some manipulator, maybe some joystick, or maybe some human operator given the trajectory, or you have trajectory generator. But anyway, the reference is like a smooth signal, what you have out from application. And then you have disturbance, which is rather unpredictable. You might assume some bounds for frequency and for amplitude, but it is coming from, let's say, environment. And they are not coupled to each other, but they are both contributing to the control error. And what is the transfer function between the reference and error? Is expression 1 over 1 plus L. And what is the transfer function between disturbance and error? It is P, our plant, over 1 plus L. But the sensitivity function 1 plus L is sitting there and there. We can recognize it. And if we say we want to have our control error E possibly equal to 0, we will have 2 reference multiplied with 0, right? And our, sorry, this is a typo. It should not be V, but D, the same, okay? And D multiplied with 0. But the reference is not 0. And disturbance, if we are talking about the real world, is not 0. What does it mean? It means that we are imposing that our sensitivity function should be possibly equal to 0. But it is not possible over the whole frequency range. Okay. So at that point, when we saw that there are some natural restrictions, and this situation of shaping the loop is rather ideal situation, I would like to give you a bit step aside just to explain what can be in plant hidden dynamics of the loop. And again, it is rather academic example, but it will give you a bit more ideas thinking about robotics. What does it mean, hidden dynamics or not modeled high order and high frequency dynamics? Imagine you have some robotic joint, okay? And imagine it is stiff. So we have the gear transmission, and we have, let's say, actuator or motor motion in the coordinate theta, and the output of the link is in coordinate q. And if we say that we have already compensated by model-based approach for some terms like gravity and maybe Coriolis centrifugal, and we have decoupled also the state-dependent inertia metrics, so we can approximate it for feedback control in the mass simple cases to mass system, because actually the coordinates q and theta are connected by the gear reduction ratio. But there is no additional degrees of freedom. So it is actually like the same coordinate, okay? And in this case, if we are neglecting all elasticities, we have just a single lumped mass and damping system, because we are assuming some inertial term of the side of the motor, of the load, and we have a q double dot acceleration, then we have the damping term also accommodated together, and then we have u is input force in generalized coordinates, rotational or translational, doesn't matter, depend on our manipulator, okay? But most important, we can see from input force to output velocity, not position velocity, it is first order system. Now imagine, and this is classical approach, you can find it in a lot of robotic literature, and think about some textbooks like by Mark Sponk and co-authors. If you are incorporating elasticities inside of such robotic joint unit or mechatronic joint unit or any type of mechatronic drive unit, then we have additional degrees of freedom, because now between theta and q, we have also rotary spring. And then we can no longer consider it as lumped mass system just with one mass. We have the set of two equations, right? So we have one equation for actuator part is given here, and another for load part, which is given here below. And they're linked together through the corresponding spring and corresponding transmitted force, okay? Why we're incorporating all the stories and why we want to understand what is going on between the stiff design and let's say design with elasticities, because now if we look into the transfer function between input force U and output velocity Q dot or theta dot, we can distinguish three cases. First case will be we are neglecting elasticities, we will obtain first order system. Okay, we call it G1. If we have some elasticities, but we say it is detectable, in which term it is detectable, it means that the stiffness is not so high. We can say that our stiffness stiffness coefficient K is just larger than M and capital M. But we can also assume that we have some hidden elasticities, because we will assume some very high stiffness of the spring, meaning that the K is much larger by several orders of magnitude comparing to both masses. And now we will distinguish these three cases, G1, G2, G3 as three transfer functions. Okay. Let's have a look what we can recognize in frequency response functions. This is all numerical simulations. You can do it easily on your own with MATLAB Simulink. In the first case, G1, we have first order transfer function, and we have then roll off, and we see how this green line is progressing. In the second case, we have already resonance peak, right? But it is rather in low frequency range. G2 is blue line. And if we look on G3, we have actually in the amplitude the same resonance peak, but which is sitting much far to the right. And this is exactly what can be hidden or not detectable or not modeled part of the system dynamics. Why? Because imagine just you need to recall the Nyquist-Shannon sampling theorem. You should think about the practical identification of the system at hand. And then the question is, what is the frequency spectrum where we can get some realistic data for model? And if our resonance peak will be too far to the right, then it is like hidden for us. And just to convince you, let's see the same G1, G2, G3, not frequency response, but step response. If you will apply the step to the U of the system G1, you will get green line. If you will excite the system G2, you will detect some oscillations, right? But if you will excite the system G3, which is actually oscillatory, not first order, but higher fourth order system, then in the response, we see nothing. We see nothing because the natural frequency is so high. And then maybe here at the beginning, we have some small transient oscillations, but well, from some identification in time domain, who will claim that it is detectable. But it is there. And once you will design the feedback control, you will face some phase deficits, some stability margin deficits. And in the worst case, with system G3, one can easily make some unstable controller, or at least controller which will produce some, let's say, parasitic oscillations, and will be some fatigue effects for hardware and for some mechanical parts. Okay. So let's talk now. It is a good point to talk about the stability margin and motivating illustrative example. Again, I took it from classical textbooks, what I'm using in my classes, what I personally, let's say, professionally like. So we can have situation where we have sufficient gain in phase margin, but the stability margin will be poor. And now let's think about the loop transfer function. Like here, you could imagine you have something in the numerator and you have some resonance, anti-resonance response, but then maybe you have only like integral controller with additional lead controller and low pass filter or whatever else. So this is a loop transfer function given here. And if one will start to analyze body plot, one will detect, because we need to look on the crossover frequency and then go down to the phase response, we will have enough phase response. And we see that we're actually not crossing minus 180 degree. So we have also enough of the gain margin. So both are actually nice. But if you apply the step excitation and look on the step response, we see it is oscillatory. What's going on? In the body diagram, it is not directly visible. But in the Nyquist plot, which is actually the same as body diagram, but just not in the linear coordinates, but in the polar coordinates, we see that we come much closer to the critical point of -1 just because of this part of the shape of the open loop transfer function. So it means that in higher order systems, and oftentimes, just to look on the gain and phase margin can be not enough. And the question why? Because we can have uncertainties into the system. And very well known, if you are talking about the classical design of feedback controllers in frequency domain, imagine you have some multiplicative uncertainties, you have additional delta P, and if your nominal loop transfer function L, as shown here, is progressing in that way, and you think you are quite far from critical point -1, imagine we have additional multiplicative uncertainty, which is not known in the phase response. That's why we need to consider the worst case, such circle, traveling alongside our loop transfer function. So we have the range of uncertainties. And now it is the question, how close such disk will come to the critical point of -1? And if we will be encircling this point of -1, in the worst case, we will get unstable system. And this is not a big mystery, because imagine you have some nominal design for some manipulator, for some mechanism, some robotic system, whatever else, mechanical system, where you have been designing system for nominal mass. And you have had some nominal payload, whatever, 10 kilogram. And suddenly you are facing the situation in the application where you are changing the payload. And suddenly your inertia will be like twice, like not 10 kilogram, but 20 kilogram. And all these things, also with uncertainties in damping, in stiffness, additional amplification gains, will in one or another way end up in your uncertainties, and then the robustness will be just lost or not given. So we should think not only about some nominal numbers, but also about the, let's say, robust design, and the stability margins are exactly given the way how to capture. So additionally to the gain and phase margin, one can consider the so-called stability margin, and how one can imagine what is it. It is actually the shortest distance, here denoted by S subindex M, from Nyquist plot to the critical point. So you see that this distance from loop transfer function in blue line to the -1 is traveling with increasing frequency, and the shortest distance will be your additional stability margin. But how can it be expressed in terms of the transfer functions? And from sensitivity function viewpoint, we can have the measure, we can have some additional metric, which is actually the maximal value of the amplitude response of our sensitivity function, because we have sensitivity function S, we have the transfer function of the plant P of controller, so altogether it is L, loop transfer function, and if we take the maximal value over all frequencies, then we will get this capital MS, and actually this distance S small m is inverse of MS. What is the message out from it? If you know the sensitivity transfer function, and this is a typical shape, so at the lower frequencies we are expecting we are going in ideal case towards -infinity decibel, or in absolute values we are approaching 0. Then we have unavoidably increase just because of duality of closed loop transfer function and sensitivity function, equation I have been writing 2 slides before. And then we see that this peak of sensitivity function is very characteristical for the reserve of robustness. Because now you see that MS inverse is actually our distance. So larger will be this peak, closer we are coming to the critical point, and in the worst case, we can also lose the stability. Okay, so now we have seen that sensitivity function can be very representative and let's say very conclusive about the stability and also about the expectations on the combination of performance and stability. And now at that point, it's good to talk about the impedance control and compare the impedance control with all such analysis and use of disturbance sensitivity function. Okay. So what is the idea? And this is already the part of my work. And what I will show you today is experimental case study. I will also present in the late June by European Control Conference. We can think about the motion control stiffness. What does it mean? Motion control stiffness, kappa, will be actually the partial derivative of all overall net forces acting on controlled moving body, derivative with respect to generalized coordinate to displacement, okay, for some time going to infinity. And if we are focusing, and mostly for mechanical systems it is the case, if we have the matched disturbance force, so meaning that our F is actually superposition of actuation force U and some external disturbance force, capital F, okay? Then by fixing some, let's say, controlled operation point for U and X0, and for consideration of low frequency range, we can go for kappa from generic partial derivative equation into Laplace domain, and then we will have transfer function between X and F. And this idea is not new. If you look in some works by Anderson and Sponk, I think 98 in transaction automatic control and introduction of impedance control approach and so on, you will find also this way of thinking and how can we analyze it also in frequency domain. Now coming back to the impedance control, we need first to understand, not to understand, to recall, because everything is quite well known for robotics. What is actually impedance operator? Impedance operator at large for mechanical systems, for let's say action and counteraction. Impedance operator in Laplace domain Z is actually the ratio between the force and velocity. And now if you have the pair of robot and environment, then through some port variables, you are connecting actually the forces and velocities, because one is the flow and another is effort. Okay, because think about the mechanical power, which is just the product of generalized forces and velocity. If you then integrate it, you will get the energy. Okay, and for impedance operator in Laplace domain, you can have different, let's say, expressions. You can specify your impedance of environment, but also impedance of your manipulator. And very simple illustrative example, once again, I take this reference, this textbook by Sponk, Hutchison, and Vidyasagar. Mass spring damper system, equation in time domain is here. And then in Laplace domain, thinking back what is impedance operator, it is force over velocity. Okay, then we have Z, which will be ms plus b plus k over s, so integrate. And now, physically, with such simple expression, one can have quite a lot of typical, let's say, typical ways of how to describe impedance. Because if we will have the poor inertial impedance, it means for s going to 0, for low frequencies or for steady state, this overall operator Z will be equal to 0. Just you are substituting s equal to 0, and you have only the first term. It is 0. Okay. If you have the resistive impedance. Think about some body moving in viscous medium. So you have some mechanical resistance. Then you will have, for steady state, z is equal at 0, you will have the term b. And b can actually be variable between 0 and infinity. So it depends on the resistance. And if you are moving some body in the air, you have lower b. And if you put it in some viscous fluids, then you have higher b. And think about some soft materials like rubber. Okay, you come in touch and you have still some viscosity. If you are staying in the viscoelastic region. And you can have also, due to the stiffness, due to the spring, because any type of mechanical contact, I'm touching with my hand this desk, and still I can assume some very high stiffness of this object. And this is exactly happening if your robotic manipulator is coming in touch with some fixed and let's say stiff body. And then you have the capacitive impedance. And for steady state, it is going to infinity. And this is exactly behind this mystery why very well-tuned motion controllers for robotics, once coming in touch with stiff environment, can start to oscillate and produce some limit cycles because of the capacitive impedance. Okay. And now we will try to link this way of description of robotic manipulator and also environment in terms of impedance with already very well known and introduced and used notation of disturbance sensitivity function. But before to do it, we need again to recall what is actually for frequency domain in terms of disturbances, what is actually our disturbance sensitivity function. Let's compare the open and closed loop with one and the same disturbance. If we have open loop, we have controller C, we have the plant, and we have the matched disturbance D. And then we are assuming output Y or L is output for open loop. And now we are closing the loop with the same P and C. We have the negative feedback, and we are considering output YCL. And another nice interpretation, it's not a property, but interpretation of sensitivity function is actually that sensitivity function gives us the ratio between the output of the closed loop system and output of the open loop system. It gives us indirectly the indication what the closed loop control system can additionally enable with respect to disturbances. So it means the disturbances with frequencies, for those frequencies where our sensitivity function amplitude response will be lower than 1, then feedback was attenuating such disturbances. But if we have sensitivity function amplitude response larger than 1, then such disturbances for this range of frequencies have been actually amplified. And this is exactly interpretation also very well known from the textbook of Fourier, no, sorry, not Fourier. Okay, I'm sorry, I missed here the point, but it is exactly interpretation of logarithm of sensitivity function here. And the sum of all this logarithm of the sensitivity function should be 1. So it means that at lower frequency, if you improve, then the integral in total will be equal to 0. Then you are like getting worse performance at higher frequencies. But the main message here, looking on this diagram, that for lower frequencies where S is lower than 1, so in logarithmic 0 decibel, then you are improving. But for frequencies where S is larger than 1, you are like amplifying disturbances. So there is no wonder. There is no ideal disturbance attenuation for the whole frequency range. Okay. And the feedback control error is actually, again, the superposition of control error related to reference and related to disturbance. And ER is sensitivity function multiplied with reference, and ED is disturbance multiplied with sensitivity function with transfer function of P of the plant. So now I got it. What we saw here is body integral. So body integral and interpretation of the body integral, what we see here in the diagram to the right. Okay. So example, how we can interpret now the closed loop response, GYR, from reference to the output is a blue line. If we have had the plant with a green line, and now we see what is in the closed loop transfer function, C multiplied with P multiplied with S, and we see, okay, we have the second order system. So it is what we expected, what is ideal case by specification. Closed loop transfer function in some ideal specification can be seen as a second order system with natural frequency omega 0, and correspondingly here I have the critical damping where I see that my zeta damping is equal to 1. And the sensitivity function multiplied with P is actually starting from 0 decibel and then progressing and then coinciding with plant transfer function. So the combination of the blue transfer function and red transfer function give us the relationship for the same controller, what can we expect for reference tracking, and simultaneously what can we expect for disturbance rejection. Okay, so what is in disturbance sensitivity for motion control? As I already said, we are considering it in Laplace domain, and we had this operator kappa. And we have also, not we have introduced, but it is very well used for impedance control and force control at large, the impedance operator Z. And both are linked to each other actually by derivative, just by multiplying with S. And then the disturbance sensitivity function as specification of impedance control can be very well used, because what does it mean out from this relationship? What is sensitivity function? It will be the ratio between the output displacement of robot and the input force. So we can say it is specification. So by means of sensitivity function, we are specifying how our controlled robotic manipulator should react to impedance. And we see it here that S is actually inverse of kappa tilde, and it is inverse of Z multiplied with S. And out from that, we can say that generic impedance control can be done based on disturbance sensitivity function. Why? Because if we have the specification, if we know how sensitivity function should look like, and if we know what is our planned P, then the, again, kind of ideal controller, impedance controller, will be expression P minus S divided by S multiplied with P. And now let me give you two, say, typical examples for contact environments, okay? Because you can imagine you have a kind of dashpot. You have a standard viscous model between X displacement and F. And it is given actually by X dot multiplied with alpha, you will get F, okay? And you could have also viscoelastic contact. So you have stiffness and you have viscosity. So it is what is known by applied physicians, Kelvin-Voigt model on the right. And with two such types of contact environments, following this idea of generic impedance control, we will directly obtain what is description of impedance for viscous, it is alpha. And what is description of viscoelastic dashpot and spring, it is alpha plus B over S. And next slide, I will show you how then the control will look like. But first of all, if we have designed the controller based on specified contact environment, and out from contact environment, we know what is the disturbance sensitivity function. We are using this S as a specification. We should recall that if we are considering the ideal motion controller, the stiffness is going towards infinity. So what does it mean? It means that if I am moving the object with ideal motion controller, and then I face some contact, then my ideal motion controller should be forcing to go through this this object. So any type of obstacles, we should either like break or move away. We don't care about the contact. So the stiffness, such, let's say, position controller, ideal position controller is absolutely stiff. At the same time, if we have some ideal force controller, it should maintain, it should keep the same contact force if I'm touching environment and not, let's say, penetrating the environment. So there are like two boundary values for the stiffness. Ideal motion controller has infinity stiffness, and ideal force controller has zero stiffness. And impedance controller, we can say it is something in between. And now if you will design different type of controllers like viscous or viscoelastic, the question is also how can we switch between it, and can we use the standard, let's say, approach, this disturbance sensitivity function, because actually we are switching. So we are coming to hybrid control systems. Just short reminder, what does it mean, hybrid motion control? Again, one of the textbooks is here, plenty shown in state space notation. You can have also some saturations, whatever else. But then you have a set of controllers. And then you have additionally the selection strategy, which is a part of control. So it means it is not only to design controller 1, 2, 3, 4, n for different environments or for different operation modes. Imagine you are doing motion control and then coming in touch with environment, you need to switch to the force control. You need also the selection strategy. So you are ending up with hybrid motion control systems. Again, I give here just for the sake of interest, have a look on some, let's say, survey and tutorial papers of hybrid motion, not hybrid motion, but hybrid control modeling, and how to apply the continuous and discrete switching logic, and how to pass from one state space into another with guards and reset and so on and so on. And for the case of consideration of such stiff and viscous controller, following the design I showed you here, this C is actually P minus S over S multiplied with P. We will end up with two types of controllers, which is one is stiff, CS, and another one is viscous. And you see that the controllers are quite different. We have CS and CV. And after that, if we will go for switching between both, we need to understand what will happen when the disturbance appear. Because any type of switching implies some jumps in the state. For example, you have think about the playing billiard and some bouncing ball effects. You are impacting the stiff obstacle environment, and suddenly your velocity switch from, let's say, x dot to minus x dot, right? So you are experiencing some step in the state. But what is also important is actually what your controller is doing. What will be your control signal? And now the transfer function between the disturbance and control signal U is this expression. And to be able to prove that the switch between the stiff controller and viscous controller will not produce some unexpected and undesirable resonance peaks, we are just considering for both controllers CS and CV this transfer function. And we see that at least at steady state in the broad range of frequencies, they're coinciding with each other. And then it is a viscous controller which is continuing the constant value, and stiff controller which has a roll down effect. Evaluated in the time domain, the switching between CS and CV produce the following. Imagine you are now moving with some constant velocity. I take the object in robotic manipulator hand, and I'm moving with constant velocity, and I have some resistance, an actuator, some friction, whatever else. And then in steady state, I have the value U, and then suddenly my disturbance is appearing on the way. What does it mean it is appearing on the way? I'm coming in touch with contact. Suddenly my disturbance D is not experiencing, but producing the stepwise impact on the system. So I will have the step here, and then I will get the effect of repulsion back. And then once I have been switching at the time point 0.1 where disturbance is appearing between the stiff control and viscous control, after such repulsion back, I am continue to converge, and in ideal case, I will just stop. So from frequency and time domain analysis, we can like guarantee or we can prove what happens with our control signals that we are not starting to oscillate or to experience some divergent and unstable behavior. Okay, so time is progressing. I think now it's interesting to see some experimental results, and I will show you the case study based on the theory basically I explained in the second part, impedance control versus disturbance sensitivity. What we have been doing in my lab in Agder, there is an actuator, 1 degree of freedom, and it's this actually electromechanical system where you have the system description given by Wolff's differential equation. You can imagine it is some lumped moving mass. We have some additional gravity, and we know it, we can pre-compensate it because it is state independent, so it is just the constant gravity term. We have additionally unknown disturbances D, and we have some additional actuator dynamics, so first order actuator dynamic with time constant mu. So here technical data are given, sampling rate is quite high, 10 kilohertz, and actuator time constant is quite low. It is voice coil motor type actuator. And of course, we need the velocity. If you're implementing any type of controllers like PID or PD with differential path, and then we're applying low pass filter to discrete time derivative. And after that, you will have approximately your velocity x dot is what you get out from this second order low pass filter. Just to give ideas about very high level of the measurement noise, because in this case, we are measuring contactless. We have inductive sensor sitting on the bottom. And then we have some adjustable mechanical tool, I will show you in the video, where the tip of the tool is the position. You can think about the position of the end effector of your manipulator, okay? But the measurement noise is relatively high. And if you see discrete time derivative dx over dt with two different low pass filtering characteristics, 1000 hertz and 100 hertz, we see that there are some periodical disturbances. It is due to the coil arrangement and voice coil motor starter, not rotor, but anchor configuration. And still with low pass filtered signal x dot, we are going for standard design of differential parts of controllers. The controlled motion is quite low in the range. It is roughly only about 15 millimeters. And now you see already the setup with adjusted additional tool, which looks like knife, but it is rather to have the, not too sharp, but some tip. And after that, we will impose to move such a tool and come in touch with soft objects. But first of all, if my video will start, I hope it will. Let's see. No, let's restart it again. Maybe step back. Aha, now it works. So it's only the motion control and going up, and after that going down. And again, important to say that there is no sensor sitting in the actuator itself. We are doing the feedback only by means of the displacement measured contactless with such inductive sensor sitting on the bottom. Okay, of course, as I already said, for such design, you need a kind of nominal transfer function. And the transfer function can be identified in frequency domain. With blue line, with blue dots, you see all points of single sampled frequencies. Mechanical system cannot be excited with very high frequencies, but still you see here roughly like 3 decades. And the plant is very, very simply modeled because from our input voltage V, we are substituting constant disturbance to the gravity to obtain linear approximation. And the model is just second order system, some gaining factor K and time constant tau. And you can recognize between the fit of the linear model and the measurement that in frequency domain, we can capture we can capture basically this integrative behavior and then corner frequency. And first we had decade by 1 decade decrease, 20 decibel per decade, and then 40 decibel per decade. Okay. And now this methodology I showed you before, this disturbance sensitivity function, we are designing 3 controllers. One will be like stiff controller, admittance controller, because you can have impedance controller, admittance controller, like inverse to each other. And then the transfer function is given here. And the characteristics of sensitivity function of such stiff controller are shown here on the red. Okay. So it means it is very insensitive to disturbances appearing at low frequencies. And if you have the stepwise contact disturbance, then we are rather interested what will happen here at lower frequencies. If we are designing viscous impedance controller, this is a blue line. We see that it is like inverted behavior to the stiff admittance controller. And we can have also something in between, viscoelastic, where we are assuming both the viscous behavior and spring stiff behavior. So we have designed now 3 controllers, and transfer functions like specification for these controllers in terms of sensitivity function are shown here. And now let's show me example, experimental result, where we are comparing the stiff, because actually, looking back here, we can recognize that it is a kind of PID controller. We will compare the stiff controller with viscous controller to not penetrating into the object. So let me start the first video. Again, once back. So now, so we are moving up with the same stiff PID controller. And then we have some break in the reference, and we are placing the half of the grape. And it's not because I'm now here in Italy, but because the grape has this nice properties. It is soft, but at the same time, it is penetrable. If you will press too large, you see here some small droplets of grape juice coming out. And this is exactly the situation. Think about some medical application where you have been forcing some soft human body tissue and you have been broken. And now we have reconfiguration from stiff controller, same one PID, to come down and at the contact to operate the system with viscous, let's say, soft controller. So another half of the grape. So we stopped here. We are not imposing to go through because our references was going down, and I will show you in the diagrams how it looks like. And this is exactly the diagrams of 3 controllers. We have the reference trajectory, we are on the slope. At the top, we have some settling phase, but PID controller is very simple. We are not compensating for some additional disturbances due to voice coil motor or friction, whatever else. But still, we have the flat phase where we reached our reference position. Then somewhere between 6 and 8 seconds, we have put the grape. And after that, with the same controller, we are going down. And here by arrow, you see exactly the time instant where we came in touch with such grape. And now, in the first case of the stiff controller, red one, we have been really penetrating and going further on and following our reference, because the ideal motion controller is like absolutely stiff. It doesn't care about any soft obstacles. In the second case of viscous controller, we have been even slowly, not slowly, but very shortly repulsed back, and we have this blue line. And if you want to have viscoelastic controller, then with some set of value for combination of stiffness and viscosity, you can impose some constant contact force on the object. This is visible here in the pink line. And interesting is also to see what's going on in terms of the control signal, because this approach is absolutely sensor free. We have no 1-4 sensor. We are only analyzing this nominal model, with nominal conditions for transient response, steady state response, what's going on the level of control signal. And now we see that we are staying in some band, and all three controllers before penetration or before contact with soft object have the similar sample. But then the stiff controller at one is going into the penetration. So it is going below some threshold value minus capital U, which give us the event to switch between both controllers. And you see how the viscous controller is behaving after repulsion. It is keeping, in average, 0 control value. It is like the robot come in touch, is repulsed back, and then staying still on some small distance and proximity to the object. And the viscoelastic, as let's say something in between the stiff and soft controller, is keeping the constant value of the threshold control signal, which is here given by pink. And this is actually on the picture the end situation. For the stiff controller is penetrating, the viscous controller is repulsing back the tool and not penetrating and staying in the contact with environment. So here are just references of what I have been showing you and some literature what I have been using and some references of the work, my work where you want to find more details about experimental setup or what will be shown the end of June by European Control Conference. And at that point, thank you very much for attention. I took a bit longer time. Grazie per l'attenzione. And I have shortly to acknowledge, because during my sabbatical period at Politecnico University of Bari, I am financially supported by Nest Foundation. So this acknowledgement. Thank you very much again.